Well, it's really great to be here, seeing some old faces and new faces, and think back to me starting out as a young boy from Welkom, walking around this campus, not knowing what the hell would be ahead in my future. And it's wonderful to be celebrating this amazing achievement that is NASSP. I need to be here. Great. Yes, so what we've seen in some of the talks is just how much effort there has to that goes into creating something like this, and so much of it, the vast majority, is sort of in the, behind the scenes by people not seeking the limelight, just seeking to passionate about building up development. And I have been incredibly lucky at virtually every moment in my career that an opportunity has come up because of such people. Putting things in place. Maybe it was 10 years ahead, maybe it was a year ahead, but I'm incredibly grateful that I get to do what I love, thanks to the dedication of so many. And we've seen that in some of the presentations, so I'd just like to express that. Rather than step through my career since 2004, when I was spending a lot of time looking for parking as an undergraduate here at UCT, I think it's still a problem, right? I'm not going to step through every stage of my career. I'd like to talk specifically about this amazing project that I stumbled into, again, a lucky break here and there, which is the Event Horizon Telescope, which brought us the first image of a black hole. It's been simply transformational. I spend most of my time working on Meerkat, and I'm not just saying that because my grant holders are in the room. I do, but I do spend and have been part of this amazing global collaboration that I've learned so much from. And I want to share with you a bit about that. I'll focus more on that, and I'll bring in some NASSP aspects. And the reason I want to do that is because I think it's fair to say that without NASSP, there would be no South African participation so far in the Event Horizon Telescope. And maybe starting with that, I'll start with Renee Krotwaterberg's notes from a NASSP extragalactic course showing, it's a photograph of a badly printed set of notes. No fault of Renee's, it was mine. But that's M87, which you can not see. And you can still, the notes are still in Spanish because you just come from Guanajuato, right? Still translating. And you can see that the constraints there are roughly less than a milliarc second. So pretty incredible that, unbeknownst to me, from reading those notes at that time, that I would later be part of the experiment that imaged this supermassive black hole at the center of that, right at the base of that radio core, resolving it with an effective angular resolution of about 20 microarc seconds. So, it was fun to go back to these notes and think back. It was also fun, and I would have had no clue at that time that my students and I would actually make an image of the same object with Meerkat more than a decade later. So it's been quite a ride. In terms of the Event Horizon Telescope results, I have to thank three incredible people that have just been just so smart and so dedicated. India Natarayan, who sadly I lost to the Black Hole Initiative in Harvard. Tariq Fletcher, who's fortunately come back to astronomy. He's a postdoc at Soraya, and Sinkosi Simelane. So these have, they've gone above and beyond as postgraduate students, and then as postdocs, and just done incredible work. And without them, no way that South Africa would have been able to make its contribution towards the Event Horizon Telescope. It was a small team because it's difficult to motivate money away from Meerkat, but fortunately Soraya was supportive of that. And then, of course, a huge thanks to the entire EHG collaboration, which it's been a pleasure to be a part of. So I have to say, just very quickly, first inspiration to join the EHT. Renee went to a conference, and I taught 2 weeks of your lectures at the third year level. And I was excited about this project. I'd read about it somewhere, and I decided to sneak in a slide on the Event Horizon Telescope, complete with a typo. But that's it. Talking about the experiment, and they're just very early stages. Shep and his team were kind of really building things up. But that's where I kind of really first heard about it. I got an opportunity from a South African, Jonathan Weintraub, who's based at Harvard, invited to a conference at the end of 2014. And then the following year, I moved to Rhodes for a postdoc, and Justin and I were in the Rat and Parrot talking about possibilities. As you know, center of the radio astronomy. Where is Justin? Center of the radio astronomy universe. Right, so I've got to go quite quickly, unfortunately, but the primary science here, you know, the raison d'etre is imaging the center of a supermassive, two very nearby supermassive black holes. And this is a simulation zooming in on the accretion flow. There can be jet activity, but right in the center there, you have this dark feature, this deficit of light that was predicted a long time ago. And then people started realizing that maybe with very long baseline interferometry at very short wavelengths, you might be able to get in there. So there are two key concepts. You've obviously got light being deflected by the distortion of the local space-time. And then you've got the concept that Moses said he absolutely hates and why he won't study black holes, and that's light being captured by a black hole. Sorry, Moses. Moses' worst nightmare. We've got photons moving around a black hole. Some of them are being deflected. Some of them are getting so close that they're actually orbiting around the black hole. And that capture and that combination of that deflection, if you look at that, predicted to cause this very distinctive signature, a deficit of light towards the center, brightening on the edges, predicted through general relativistic magnetohydrodynamical simulations and confirmed with observations in 2019. The only snag is numbers on the bottom there. One of them is squared. It's the speed of light. It's quite large. Distance to nearest big black hole, far. So you really need very, very massive objects, the M on the top, to have any hope of capturing this. And so for the most massive black holes that we know that are the closest, the largest photon ring size that was predicted is M87 and Sagittarius A star of order a few tens of microarcseconds. So a quick thing on technology and techniques. You need basically your antennas separated by an Earth diameter, of order an Earth diameter to get there. There's no other way of doing it. The other slight snag is you've got to put those as close to space as possible, preferably in space. But these things weigh thousands of tons. Their surface accuracy has got to be good to an RMS of order 40 micron. So it's really, really tough to do that. So you've got to go to some of the more extreme places on the Earth. I'm unfortunately covering Antarctica, but you can see, I think this is part of what attracted me, just the sort of extreme interferometry of it. But in essence, you're using this global array of shards of glass put in strategic locations, using the Earth's rotation, trying to image orbiting plasma far away that is roughly the apparent size of the moon, a donut on the moon. And our small team, South African team, our contribution to this was leveraging a lot of the effort that had gone into Meerkat in modeling systems. There you're modeling for a large N, 64 elements array, in basically modeling the transfer function of everything that can go wrong, how your instrument influences your inferences on scientific parameters. Interestingly, a part of that was also optimizing the array down the line, but we'll return to that. So in essence, a lot of the reason we were doing this was for the model comparison and parameter estimation. So this is not an actual fit. Don't be alarmed. This is not how we do things in the EHT. It's a pedagogical part of the paper that just illustrates the different visibility amplitudes you get at different baseline lengths, the visibility being the fundamental measurement of interferometer, for different shapes. And the prediction was a crescent or ring-like object, and so there is a distinctive pattern in the visibilities there. And we were geared towards to doing this. And to doing this properly, building up posterior probability distributions of measurable parameters of interest and trying to constrain the properties of the black hole and the accretion flow. My first foray into probabilistic methods was actually NASSP. I was lucky to have some great tutors, Michelle, Roz, and Ed. And Ed, in René's course, ventured into teaching us Markov chain Monte Carlo. Now, the honors NASSP students of today will be like, oh, I do that every second day. But back then it was, it wasn't just import EMC. You had to write it out yourself, and Ed took it upon himself to teach us that. It's really cool. And clearly an amateur not using a burn-in, which Ed is pointing out there in his grading. And I also, Ed, you seem to have missed it. I mean, this was high-pass data, but we seem to have messed up the... got the slope right, but there's something wrong there with MH1 star. Right, so the flagship results that you've no doubt seen, these two black holes, one larger than the solar system, one fitting Mercury's orbit inside of it. Just incredible to have two objects that weigh more than 1,000 times difference, and they look very, very, very similar. I mean, that's partly just our poor resolution, but black GR is just holding at these factor of 1,000 difference in scale. Just incredible objects. It's not just been that. There's been a huge technical success in the image in the middle there, which was polarimetry of M87 star. This was a huge effort, and there is an incredibly talented group of graduate students and early career people inside of the Event Horizon Telescope collaboration. That's obviously key because launching jets from black holes, magnetic fields we know play a key part, but actually getting horizon scale measurements of this is absolutely fundamental to understanding the Doppler shifted jets that stem from this, M87 being one particular example. And as you might have seen last week, despite the conspiracy theories that we faked it, we repeated it with data taken a year later with an expanded array, so you can see a slightly enhanced brightness there. And what's interesting, the consistency, and there is this slight change in the position, azimuthal position of the brightest part, and this is kind of more what we expect with a larger scale structure of M87. I don't really have time to go into a lot of this stuff, but it's interesting, given some of the emphasis in NASSP, certainly in the early years, testing different alternatives to both gravity and different alternatives to black holes. And there's some pretty basic tests that we can do already, but it's really the expansion of the array that's going to put these two, test them in even far firmer stance down the line. But what's interesting with an experiment like Event Horizon Telescope is once you build up some interferometric expertise and you have a strong relativistic foundation, which I don't have, but the collaboration is obviously filled with, you suddenly start to compare things on scales with experiments like LIGO. And on the one side you're testing consistency with general relativity. On the y-axis you've got a fractional deviation from GR. This is not my wheelhouse, but some will know how to formulate these. And you're being able to test that over 8 orders of magnitude in mass. So really leveraging a lot of the skills that we've developed as part of the Meerkat project to do some really fundamental physics far beyond that, I think is one of the things that the Event Horizon Telescope has a real niche role to play. And of course, the square kilometer array will do a different part of that through pulsar timing. I didn't do GR as I revealed. I was an electrical engineer making the transition. In fact, I have to thank Patricia and Renee, because when I was selecting my master's courses, 5 courses, I had plasma physics and quantum mechanics, thinking I needed to bolster my physics as an engineer. And you gently steered me towards space tech, which was more my wheelhouse, and I'll come back to that on the final slide. But my brother did try his hand. He was 8 years older. He is still 8 years older than me, and I'd like to think maybe 12. He did try Peter's course back in 1997. I don't actually know if he survived. It was a slight digression from chemical engineering, but then again, I took a huge digression from electrical, still on it 2 decades later. In terms of broader impact, this is incredible thing of the Event Horizon Telescope. So to make the above the fold for these three publications, and apparently this number is credible, but apparently over 4.5 billion people saw this image. And of course, I mean, pick your favorite, but this is probably wave 4.4999 of the. But more seriously, making it into, you know, some of the most prestigious art museums in the world. We know of our cultural impact in astronomy, but it's quite interesting to see it, tangible examples such as this. And then, of course, you know, when would you see a telescope director like Chef Dolman be on the same red carpet as Lenny Kravitz? Come on, this is cool. This is a cool experiment. I had a slightly lower key event than Mark Zuckerberg at the Wits Planetarium, trying to promote funding it around the same time. Now, I have to step towards the future before I run out of time, but there is a very bold plan to make a transformational step. I know that's a buzzword, but it really is seeking to do a transformational step in black hole imaging, and beyond that, broadening the science case with millimeter VLBI. So this is called the Next Generation Event Horizon Telescope, just like the Next Generation VLA. And you can see a substantial increase in the number of sites, but all sort of centered in certain time zones, almost all. And, you know, we really have a compelling argument to contribute this to this as the African continent. If you look at a black hole, a more static black hole like M87, this is a simulation of M87. You can see substantially enhanced resolution and imaging of the ring, but you can also tie that to the base, which is key in understanding a lot of the accretion physics and jet launch physics. But the kicker for, and the polarimetry is exquisite what you can do with the enhanced array. But the kicker is if you want to do time-resolved imaging of Sagittarius A star, which is right above us here in southern Africa, you really need to add quite a few stations on the African continent. That is the key game changer. There are not enough east-west baselines in the southern hemisphere. There are hardly any. And that's where things change. And the interesting thing here is the synergy between the intra-African baselines, particularly this. So we have AMT and STL. I won't say exactly what that is, but I think you guys can guess. That's a candidate site in South Africa. And you can see in the inner part of the UV plane, these are the Fourier modes. There are some very important baselines there for tying shadow to large-scale jet. And then there's the critical long baselines, east-west baselines, that if you want to image the heart of this beautiful meerkat image, well, you can see on the simulation I'm blocked out. But there are 3 stations on the African continent. It's really, you need at least about 3 to enhance the snapshot capability and recover images of Sag A star evolving on timescales you can see on the bottom left there. Remember, it can be as quick as, it's of order minutes of plasma orbiting around that 10 to the 6 solar mass black hole. So snapshot capability, it's critical that you have millimeter stations in the southern hemisphere, and we have a remarkable geographic advantage for that. What's interesting is you're now making images, many images, not just one. There was one image on the front of the New York Times, but you can make images of this and do tests of gravity in well, let's not say in perpetuity, but for years and years ahead. And you get different perspectives on it. I mean, we have to explore huge parameter spaces. And one example of a NASSP student that did a project with me was basically taking 100,000 simulated black hole snapshots and using an unsupervised learning algorithm to classify them. And then we backtracked and we said, okay, well, we can't inspect and do a Bayesian fitting to each single image, but we can classify them based on image features using artificial intelligence, and then exploring each of those as representatives. So Michaela did some fantastic work on this, building up this node of a chessboard representing 100,000. And then, of course, there's huge multi-wavelength and multi-messenger capabilities here. I mean, when there's an EHG campaign, Hess is looking at Sag A star at the same time, for example. And then multi-messenger, we will have an incredible gravitational wave observatory for nanohertz gravitational waves in this country. Well, we have it, and it's busy doing amazing timing. And over time, that's going to get become the premier one very soon. And so the EHT will be able to resolve the very binary supermassive black holes that are generating the gravitational waves that Meerkat is able to detect. So there's an incredible synergy there and an area for real building up global strength and bringing in the next generation of NASSPs into doing world-class science. So this is, along the lines of why Indian and I wrote this article after the Sajay Star result, and the authors of the NASSP article kindly linked to. I just want to, NASSP not only has done a lot for me, but it's produced some incredible students that I not only got on incredibly well with, but did some fantastic work and with me on various projects from honors through to PhD, and have gone on to do great things. And so, yeah, I'm very, very excited and a huge stakeholder in where NASSP goes next. So, in summary, we live in the black hole imaging era, and GR still holds. This experiment is just, it's been an enormous success off the back of some people in the collaboration working on, 4 decades just to see that. So again, I came into right at the end and got very lucky to be involved. But a huge technological success, scientific success, algorithm development, and then obviously the PR, the public outreach aspect was just, we were blown away by how it impacted people. But the expansion on the African continent, particularly on the African continent, will broaden that to far beyond just testing theories of gravity, but resolving binaries that are radiating in the pulsar band, doing incredible multi-messenger and multi-wavelength work, looking at microquasars. It's a very, very exciting path ahead, and I hope that we and future NASSPs are a part of that. And I really want to, again, just thank everyone that's made NASSP a reality, because, yeah, I've been a huge, huge beneficiary. I couldn't work it into my talk, but I have to finish with a video of probably my highlight of NASSP, which was building a 2-stage rocket, almost 3 meters in height. And we managed, I couldn't find any photos, but I found this video, and I'll take your questions. 680 meters high. Thanks to Peter Martinez. All right.